for those who've seen the museum. It's my pleasure to introduce Dr. Richard Kelley. Rich received his Bachelor of Arts degree from Rutgers University in 1977 and his PhD from MIT in physics in 1982. So he began working in X-ray astronomy while a graduate student using the SAS-3 satellite. So he's been involved in many X-ray observatories since coming to Goddard in 1983 as a National Research Council Research Associate. And then he went to NASA as a employee in 1986, just a few years ago. A year after arriving at Goddard, he began working on the development of X-ray microcalorimeters. He has contributed to the development over many years. The energy resolution started from 140 electron volts energy resolution, and today it's getting close to 1 electron volt. So that's pretty incredible. And he has led the development of these devices to put them in state-of-the-art detector arrays. And currently the detectors are flying on the X-ray imaging and spectroscopy mission, XRISM. He is the US Principal Investigator for NASA contributions to the XRISM project. He has received NASA medals for outstanding leadership and exceptional scientific achievement. He served on the National Research Council Astro 2010 Potato Survey. The study group on international partnerships. As I say, the XRISM project is a joint project with Japan. He's a fellow of the American Physical Society, and he has received the Goddard John C. Lindsay Memorial Award. That's the highest Goddard Award for space science in 2016. So let's welcome Rich.
I'm extremely happy to be here, and thanks folks for inviting me to speak. It's really given me a great opportunity to see some colleagues that I haven't seen for many, many years. You will see those who worked on this stuff in the past will see what we worked on and led to. So the title of my talk is How Goddard Space Flight Center Built the Coldest Spectrometer Ever to Observe the Hottest Objects in the Universe. And I would say there's kind of the thing I want to emphasize, especially for this audience, is just some of the incredible innovations that have taken place at Goddard, and things that many people can be very proud of. Because they worked on it and they contributed to it just because of the way Goddard was set up. It was really just a fantastic place to bring people together with the right skill sets to make new things happen. So just to orient yourself, when we talk about X-rays, right? So if you go out with a good telescope, or a very big observatory telescope, and you look up at the night sky, you'll see things like this. This is a cluster of galaxies. Many galaxies have fallen together into the potential well of all of this mass that's there. And so you can see something like this. Galaxies of different ages and different types. And if you look at this exact same thing, if you just imagine that you have X-ray vision. Okay, you look at the same spot in the sky, what would you see? In this case, you would see that. So there are some things, you'll see the one galaxy there in the middle, there's some others that line up with other galaxies that are there. But the main thing that you see here is diffuse gas. And in order for it to be emitting X-rays, it turns out that it means that it's extremely hot gas, typically tens of millions of degrees Kelvin. Now it's very rarefied, it's very, very low density, so if you were in that cluster, you wouldn't really be in any danger. But because we're seeing through so much distance and through so much space, accumulated light, X-ray light from these things is actually very bright and easily detectable.
That looks like a vortex drawing in all this other...
Yes, it probably is. It is. That's right. That's right. So all of these galaxies, they're formed, evolve. Eventually, you get a concentration of galaxies. Gravity builds up, pulls more together. You get this kind of spiraling structure.
You can really see it in X-ray, but you couldn't see it otherwise.
That's right. So, question is, how do you make progress on this? So it turns out that going way back to in the 1970s, early 70s, there was a satellite called Ariel 5 built in the UK. And I just learned from Paul Hertz about a half hour ago that NASA contributed to that mission. But it was mainly a UK mission, and it had detectors that had some energy resolution. And the plot that you see on the right side is a spectrum. Okay, so it's basically energy, or you can kind of think of wavelength. We like to think of energy for X-rays along the x-axis, and then just the flux is the vertical axis. And then you see, obviously, decaying spectrum, so there's less flux at high energies, more flux at low energies. And there's something that looks like a bump there around 6 kPd, approximately. So that was a surprise. People didn't expect that. A mission prior to this, called Uhuru, which was the first X-ray astronomy satellite built by NASA, that was led by Ricardo Giacconi, who eventually got a Nobel Prize for that work and other work, had shown that when you scan by certain sources on the sky, X-ray sources, they were extended. And it turned out that these were the X-ray clusters of galaxies like I just showed you, Perseus. So this is when this satellite came along, they looked at the Perseus and they see this bump around 6 kPd. The energy resolution there is about, I don't know, maybe over 1,000 electron volts. So not very good. You're basically measuring energies to 1 part to 6 or so. But of course, theorists get to work on this, and the conclusion was this is probably due to very hot gas that's just emitting X-rays thermally. But so what that meant is, well, to really do scientific, serious diagnostics on this, you're going to need a spectrometer with a whole lot better energy resolution. If you had that, then what's really out there with the clusters really emitting is something more like this. So you can see lines from all the different elements that are made up in the gas, starting with going from oxygen, nitrogen, all the way out to iron and even nickel. So the question is, how do you build something that can measure the spectrum with that kind of precision? This is a simulation, but how do you actually measure it? And what this led to, again, through just a fabulous confluence of infrared astronomy, astronomers and technology, and X-ray astrophysicists, was the X-ray calorimeter. And the basic idea, and then this is actually page 1 and page 2 of a director's discretionary fund proposal, if you remember those, PDFs from 1982, handwritten by Harvey Moseley and Richard Machowski. And the basic idea was to, instead of detecting X-rays in like a device that turns the X-ray into charge and you collect charge, like CCDs or functional counters, things like that, you do it thermally. So if you absorb an X-ray photon in something that turns out to be very small and very cold, you can basically create a pulse, a temperature pulse, and the amplitude of that pulse should just be proportional to the energy of the X-ray. So this proposal, I think, led to something like, I don't know, maybe $60,000 to put toward a cryostat so that one can start doing tests at the very low temperatures required to do this. And the basic idea is by being very, very cold, you get two things going forward. One is the heat capacity of materials is very low at the low temperatures. And so a small amount of energy can lead to a measurable increase in temperature. And second is by being very, very cold, you have very, very low thermal fluctuations, just noise. Johnson noise in resistors and photon noise in detectors in small crystals is very, very low. And so you can, in principle, measure the amplitude due to a single X-ray with very, very high signal to noise. And there's just a numerical example here that I won't go through the details too much, but when you kind of work through this, you use, say, an X-ray and a little piece of silicon about the size of the ball with a ballpoint pen, you can measure the amplitude of that pulse to a part in several thousand. So instead of going from 1 part in 6 that they had with the old proportional counters, now you're getting to parts in thousands. So that means, in terms of our numbers here, energy resolution of a few electron volts and noise that's 1,000 times smaller. And so how do you measure the temperature of something? And the typical ways of doing it is through resistance, changes in resistance with temperature, either in semiconductors, doped semiconductors, where you'll get a resistance versus temperature that looks something like this. very steep change, so that the RDT is extremely large. So a small change in temperature gives you a big change in resistance, which you can measure with electronics. And then also more recently, people use superconductors. Superconductors have the property, as you know, of being, say, a normal metal, and then at some temperature they go through a transition, and the resistance goes to 0. And if you work in this little step part here, this little transition area, you can get a very, very high sensitivity to temperature change. So that was basically the idea. That was back in the 1980s. And the mission I'm going to be talking about, we just launched 2 years ago. So what happened? Why did things take so long? But before I tell you that, I have a question.
Just a quick question. How did you do the spectrum? How are you going to get into, you know, how, you know, when you get the thermal, it measures the energy. How did you break it up for all the elements?
I'll show you.
You're going to get to that?
I'll get to that. I think I'll get there. So let me tell you a little bit of history here. I'll try to keep this short. So the work that started back in the early 80s was to support putting an instrument called the, had a really clever name called the X-ray spectrometer, XRS, on this mission that NASA was developing or putting together called AXAF, the Advanced X-ray Astrophysics Facility. And I have to say that the systems engineer who worked on that was Cliff Jackson, sitting right there. Thank you, Cliff. And that project went along for, you know, the sort of the second half of the 80s into the 1990s. And you know, budget realities led AXAF to be kind of, instead of one big peak, to be kind of spread out a bit. So it was divided into 2 missions, AXAF imaging and AXAF spectroscopy. We were going to do the spectroscopy instrument on that mission. And that went along for several years. And then in 1993, there was the recognition that scientists in Japan were preparing to build their next X-ray satellite. And there was a lot of discussion about wouldn't it be spectacular if it be this X-ray spectrometer based on the calorimeter on that mission. Because the timing works out well, that would save NASA money. It would be a real challenge for Japan, but it would really push them technologically to support the mission and so on. So that was adopted. That was in the year 1993. Meanwhile, AXAF kind of just became AXAF again. Just now back to being one mission. Eventually launched in 1999, was renamed Chandra, and has been flying since then and produced spectacular results in so many different ways, but basically creating very high resolution X-ray images. So Astro-E was built and launched in 2000, and there was a follow-up mission called Astro-E2. It was launched in 2005. Then there was Japan did other missions in between. And there was an Astro-H, also had an X-ray calorimeter, launched in 2016. And so that, what does it look like now? Basically, Astro-E unfortunately failed on launch, so it didn't make it to orbit. Astro-E2 failed after 2 weeks. There was a problem with how the vent gases from the cryostat, which I'm not going to get into, but the helium and neon managed to get back into the guard vacuum of the dewar that's producing all this low temperature that we need. That failed after a couple of weeks. And then Astro-H failed after 38 days when an operator sent one very, very fatal update to spacecraft parameters that caused it to, instead of, when it was trying to find the sun in safe hold, it ended up spinning so fast because it had positive feedback when the sunset thrusters was accidentally reversed, but it spun up so fast that the solar panels broke off, so it died. Now, so at all those years, still no results, although with Astro-H, we did get some really nice results on one object, in fact, that Perseus cluster that I showed. And so that was at least something that really demonstrated that this is really worth doing, pushing, keeping going. And of course, you can imagine before maybe even thinking about doing it again, one would want to know what's going to be different. And I have to say, Paul Hertz here was very much involved in headquarters at that time, but we're willing to do this again, but what's going to be different this time? What kind of assurances do we have that things are actually going to be done much more professionally and so on? And so that eventually became this mission, the X-ray imaging and spectroscopy mission. So we worked very hard on that, including through the pandemic. I won't tell you what that was like. That was extremely challenging for our team. And, but we'll see, it was finally successfully launched in just a little over 2 years ago. Success. So what is XRISM? It looks like this. It's an X-ray telescope. It's got 2 X-ray mirrors that focus X-rays onto X-ray calorimeter array. And then also a separate mirror that focuses X-rays onto a CCD instrument that's entirely built within Japan. We'll talk about that, but that's designed to produce wide field X-ray images. And this is what's doing the high resolution spectroscopy. And the way we've done this over the years is very much a joint collaboration. So we contribute the things that we do best, which is one is in the area of X-ray optics, in particular, not so much super high resolution optics, at least up to this point, but very high throughput X-ray optics. So in a relatively small size mirror, relatively low mass mirror, we can produce very high collecting areas for its mass. And basically these are X-ray mirrors work by having 2 sets of reflectors at just a slight angles relative to the vertical. So you X-rays bounce off of one mirror and then bounce off another mirror. You can actually bring all the X-rays to a focus. So this is how we get X-rays onto a sensor. These were invented at Goddard by a scientist named Peter Solomitsos back in the, I think, the late 70s, certainly by the early 80s, and has continued through its mission. And then the other is the X-ray calorimeter. This is the array, what it looks like. It's a relatively small array, but it has extremely high energy resolution. And this basically just illustrates the concept of how the thing works. For this image, we've managed to slow down the X-rays to a very small speed. And you'll see here, the X-rays come in, and X-rays hit the pixels and create a different amount of heat depending on their temperature. So in a sense, I think to answer your question, doing spectroscopy with this is actually easy. You just measure a pulsite, and then you just make a histogram of the number of times you got that pulsite, put it into bins, and you have a spectrum.
Well, the question was, how do you distinguish between the elements within that heat, if they're so close in energy? The different elements that you're trying to resolve.
Okay, so basically, for other measurements, including measurements with these devices, the transition energies, in other words, when an electron goes from one transition to another transition in a particular element, has a very well-known, very precisely known energy. And so we know, when we're looking at iron, we know what the different transitions are. So when we get a spectrum, we can usually quickly tell, okay, this is iron, it's at this energy, you see these different transitions, and so on.
So each photon has an energy that you can detect?
Yes. Every photon has a unique energy. It's based on the transition.
So you're counting photons?
Counting photons, yes. So that's kind of what this was, without me saying it, that is what we're doing. We're literally just taking individual X-rays, they're for practical purposes of a particle, and the X-ray comes in, we measure its energy precisely. I can tell you, that was from calcium. That was from a particular transition of calcium or nitrogen or iron. And now to get cold, how do we get cold? So you do things like use mechanical coolers to get down to a certain temperature, and use liquid helium to get you down to 4.5 Kelvin or 1.3 Kelvin, and pump on it with the vacuum. And then you get down to these, below 0.1 Kelvin, which is what we need to operate the detector. So you use magnetic refrigerators, or so-called adiabatic magnetization refrigerators, developed in the cryo group, and we have for our instrument, we have a 3-stage ADR cooler to get us all the way down from 4.5 Kelvin down to the 50 millikelvin. So this was basically one of the things we delivered to Japan. Is you're seeing 2 different sides of it on this plate. We have the detector assembly, the X-ray calorimeters in here. This is one of the ADR stages, and there's the other 2 on the other side. So we build all this stuff at Goddard, test it like crazy, and then we take it to Japan. And the Japanese at that point have already built the cryostat for it. So this is a doer. So have liquid helium in it and mechanical coolers. And then we show up and we put our stuff into the doer. extremely well. And then before the door is closed up, you have to put in these things called thermal blocking filters because in order to keep this thing cold, it has to basically be sealed. But you want to get X-rays in. So we have filters that are aluminized polymers, extremely thin. I like to think of these things as soap bubbles. That we want to make sure they don't pop. They're very, very thin. They're supported by a silicon mesh that you can see kind of hexagonal pattern they're supporting it. And those go in at the end. The door is upside down at that point because you don't want to accidentally drop, particles or debris or tools into the door. So that's all done upside down for a couple of days. So just to summarize, the main things that Goddard, NASA, that Goddard supported was X-ray mirrors, one for each instrument on the spacecraft, the X-ray calendar array, that came out of code 553. After many, many years of work, some of the key people in the early days, people like Brent Mott worked on that. Thus, cooling chain from code 552 to 502, and of course, instrument electronics from code 560, and we have the US Science Data Center code 600.
Are they all grazing incidents?
Yes. Yes, that's right.
Hey, Rich,
And these are aluminum.
What was the question?
the ion implants, were they for all 4 of the missions? Were they all done in Building 11? Was that
Yes.
the ion implanting there?
Yeah, eventually became building 30, but yes.
Yeah.
That's right. And it turned out that the detector that you see there for XRISM, that was actually one of the spares from Astrid, going all the way back to Astrid 2. So finally, success. 2 years ago, or a little over 2 years ago, on the Japanese H-2A rocket from Tanegashima. Really spectacular adventure just to be part of that whole process. And this was one of the rare dual manifests. So you may recall Japan had a mission called SLIM, which was going to go and do a pinpoint landing on the moon. It was really like within 10 meters or so land on a spot. And it did do that. It was really spectacular. It tipped over because it had a problem with one of the thrusters, but it did land and they didn't get their science data that they were trying to get from that mission. But we were deployed first, I think, in higher priority for Japan to recover this mission. So we deployed first, and then they went on to the moon later. And so after, obviously commissioning, you do all your critical operations and go through your commissioning steps over a 3-month period. But on day 32 after launch, it was time to go ahead and operate the ADRs, get down to our operational temperature. So you see temperature here at the detector stage, and we're using a thermometer here that's not very sensitive. It's higher temperature, but it has to be really sensitive at lower temperature. But you can see we're at about 1.5 Kelvin in space, and then we demagnetize and get down to our operational temperature of 50 millikelvin. And the requirement is to be at 50 plus or minus about 2 microkelvin. So that's, we did achieve that. So that's not just a straight line flowing, that's actually data. So I know this is a little bit hard to see, but this is one of our first spectra that we took, and this is of a supernova remnant. So you probably know stars generally after they consume all the fuel and hydrogen in the core of the star, they begin to collapse, and some, depending on their mass, will produce a supernova explosions, and then that gas goes out into the interstellar medium and can cause X-rays to be detected as the gas just slams into interstellar medium. So this is a spectrum. You can see all these lines, all these diagnostic lines. And you can't read this very well, but this is we're seeing lines of silicon, sulfur, argon, calcium, chromium, manganese, iron, and nickel. And we all know the phrase, a picture's worth 1,000 words, and some of my colleagues like to say a spectrum's worth 1,000 pictures. So, it's sort of true in the sense that there's just so much you can do with this data. I'm going to talk about a couple of things. So this is another supernova remnant. This is the famous Cassiopeia A. There's an image here by James Webb, just showing you the incredible detail of the object, and basically infrared. And then when we look at it with XRISM, we see, of course, these lines, all the different elements that have been created in the supernova process, going out to the interstellar medium. We can measure the widths of the lines, we can measure the shifts of the lines, and so we can see something that are extremely turbulent parts of the supernova remnant. We're seeing in other places it's not so turbulent. But in all cases, we can measure just lots of different aspects of the X-ray emitting gas. And the goal here is to try to learn something about the star that blew up and created the supernova remnant in the first place. And that you see here, so here's our XRISM images, or array projected onto the supernova remnant. This is with data from the Chandra image underneath. You can see here, we're looking at each pixel is basically giving us an independent spectrum of that area of the supernova remnant. And one of the interesting things is that we can look at not only the abundant elements, I've shown you there, the silicon, sulfur, argon, and so on, but we can look at the so-called trace elements, phosphorus, chlorine, potassium, and those are very interesting because those give you a real sort of handle on the fine-tuning of the nucleosynthesis process that took place during the supernova explosion. It gives people an opportunity to figure out, to estimate the mass of the star that blew up. So that's work that's still ongoing, but it's moving possible with present data. And the point being that we can measure abundances even of these trace elements. I mean, this is a log scale here. They're just really high signal to noise just because we have so much sensitivity on the energy resolution. Here, this was a big surprise. This is a X-ray binary. So we've got, in this case, this is a neutron star that's going around a companion star. And it's close enough that matter is being pulled off of the companion star and forms a disk and eventually accretes onto the neutron star, produces X-ray emission. And these have been known since the 60s, really spectacular. Some of these systems have black holes, some have neutron stars, so that's how it works. In this case, the spectrum was very surprising because it was essentially all absorption lines. So, at the spectrum you saw the emission, it was all absorption. So what's happening is there's just so much material around this neutron star, and that actually, if they're being produced really close to the neutron star, have to make their way through all this gas that's falling in. So you produce mainly absorption lines. And again, this spectrum is really complex. It's taking a long time to analyze it. What's going on, and there's basically a picture now of what the structure of the accretion disk looks like based on this. This was published in Nature recently.
Rich, is it better that they're absorption lines than emission lines? And would you have preferred them to be emission lines?
Well, it just depends on the nature of the object. So there are others that I could show you where you see primarily emission lines, and those are also, you just do other kinds of diagnostics with those emission lines.
The resolution stays the same?
Yes, that's right. In all these cases, the energy resolution is better, it's narrower than the lines that we're measuring, which is what you want. In other words, the lines are being broadened by physical processes, velocity, turbulence, and so on. We can, if we're sampling it, we're measuring with something that's higher resolution. Moving way out into the universe, this is an active galaxy, famous source called NGC 4151. Here we see a very bright neutral iron line. So this is coming from hot gas, but not super hot. So it's not all ionized. But there's other structures, absorption lines in here. And these absorption lines are not at the energy that you would predict based on just the redshift out to that particular active galaxy. So we know that there's relative motion. And then in a much better case, again, a similar source, but much better example, now looking at those lines in detail, you can see, first of all, they're shifted out to about a quarter to a third of the speed of light. And it's blue shifted. So the matter is coming toward us, and basically what it looks like it's material that's absorbing X-ray, but it's moving towards you very, very fast. So we're actually measuring blobs, if you will, of matter coming out as part of the process whereby accretion onto a supermassive black hole, and that produces jets, and the structure of these jets has material in it that absorb X-rays. But it's absorbing it in a different energy than you expect because it's highly fluid shifted in space. So that was another really interesting result, also published in Nature recently. And then going back sort of full circle to the beginning, here's that Perseus cluster again. I showed it at the very beginning, but here's now our XRISM observations. So there are more of these since then, basically. Just going out and just measuring the structure. And one of the surprises that was encountered is that the lines are narrower than expected. It was anticipated that all of this structure in the gas, in active galaxy here in the middle, all this gas moving around here, would have really broadened the spectrum from turbulence or actual just full redshifts and blue shifts. But instead, the lines are pretty narrow. So putting this together with other clusters, now we've looked at a little over half a dozen clusters now. This seems to be a pattern, so this is interesting. This is why you want to do new things, right? Because you make discoveries. And so now it looks like these clusters, that they're the so-called turbulent broadening of the gas in the cluster is just lower than models of cluster formation predict. So that's good. I'll keep it go back and revisit models and hopefully learn something new. And just to summarize, in a sense, what we know about clusters. Clusters have visible light. You see those galaxies. You saw that sort of orange X-ray emitting gas that I showed you there. And we know from other measurements and how fast the galaxies are moving and so on, that there's a much larger component, and that's due to what we call dark matter. And so the breakdown is only 5% of the light that you see in the picture of a cluster of galaxies is the galaxies themselves. 15% is X-ray emitting gas, and most of it, 80% is dark matter. And just within the X-ray emitting gas, if you go with these lines that I'm showing you of iron and so on, and you can figure out how much mass there is in the cluster. It turns out that a cluster like Perseus has 10 to the 10 solar masses of just iron. So just think about that, 10 to the 10 solar masses of iron. They're just so big. Lithium, there's gold, there's 30,000 solar masses of gold.
They're worth a lot.
So anyway, it's, the X-ray spectroscopy is one of the many tools now that X-ray astronomers have. And it's a high-resolution spectroscopy possible by XRISM that is really going to, I think, expand what we know about optics in detail.
Can you comment on the dark matter a bit?
Sure. Oh, can I talk?
Yeah. So 8% dark matter. Can you maybe?
Well, all we know about dark matter is just that it's detectable by its gravity. It has gravity, but it doesn't emit photons, and it doesn't interact really with anything except through gravitation.
Well, the comment there was X-ray emission is a tracer of dark matter. So.
Okay, I see. Yes, I understand what you're saying. So. So just that the X-ray emission, the X-rays are falling. So the galaxies, they're like by mass 5%. That 5% is not really affecting the X-ray surface brightness and stuff. So the X-ray surface brightness is really being affected by the gravitational potential of all of that dark matter. So by measuring kind of the surface brightness of an X-ray emission, that's related. That's giving you a picture of how the dark matter is probably distributed. So it's kind of indirect. But basically, the X-rays just kind of you want to know what the dark matter is doing in terms of its gravitationally. Look at the X-rays.
Hey, Rich.
Yeah.
Remind me how. I'm trying to remember back how important it is that the X-ray spectrometer, you're getting a sensitivity across a bandpass of energies at the same time, not some other technique where you have to scan through and.
That's right. Yeah, so each pixel is an independent spectrometer, and one X-ray coming in can be one energy, next X-ray coming in a millisecond later is a different energy. So you're getting the whole bandpass
simultaneously. And there were other techniques, I'm trying to remember back, you could scan through things, but then
you're not
getting
use dispersive spectrometers. Maybe you have to have a kind of a slit, and you just measure a small little strip of the spectrum of an object, and then you have to keep, move the slit on the sky to get the full spectrum.
So these have to be very fast detectors to avoid. So can you comment on how fast they are?
Yeah, that's a good question. So these detectors are, the pulse response is about 2 milliseconds. In other words, if I put an X-ray in, you saw that kind of exponential decay. The exponential decay time constant of that pulse is about 2 milliseconds. And newer generations of detectors, these are already a couple of decades old. So modern devices based on the superconducting transition thermometers that I showed you, those have time constants down to tenths of a millisecond. So it's pretty fast. It's not as fast as some detectors that don't have very good spectral resolution. You can get it down into microseconds, which is good for certain kinds of timing. But for spectroscopy, the millisecond to tenth of a millisecond is probably fine. And for sources that are extremely bright, because obviously new missions will have huge collecting areas. If you look at some of these bright galactic sources, they put too much flux. There are techniques to diminish the flux so that you can still do high-resolution spectroscopy by putting a mirror slightly out of focus or putting a neutral density filter in front. Well, what I wanted to say, just to end up here, was, so in a sense, XRISM, it's taken a long time to get this thing going. But we're there, it's working. But in some sense, it's still a pioneering mission. It's the first time we're using this new technology, this new approach to doing spectroscopy on a space-based mission. But it's really just motivating folks to want to do the next step. And the key next step is going to be missions with much more collecting area and higher resolution optics than what we're flying with these high throughput but low mass, small diameter mirrors, which only have about 1 arc minute imaging capability. But to kind of ultimately bring sort of like Chandra-like imaging with one of these X-ray calorimeters at the focal point. So now we'll be able to measure something like that Perseus cluster now with this level of detail in terms of imaging. And again, each pixel will be an independent spectrometer. So just huge, enormous data cube of information. And so in Europe, there's a mission called New Athena that's under development. Hopefully we'll launch in the late 2030s. And we are involved in that. We are leading NASA and Goddard Space Flight Center and partners at NIST and Boulder are working on an array for that mission. That will have about 2 electron volt resolution, about a factor of 2.5 better than what we're doing with XRISM, and again with a much, much higher performing mirror. And then maybe longer term, another X-ray flagship mission for the United States. LINX is one that was proposed or identified and proposed in the part of the last Astro survey. And the idea is just to basically extend this development of X-ray microcalorimeters, spectrometers up to a much larger flagship level observatory. So hopefully that will take place in the coming decades. And of course, I don't think a little bit of this work. Huge team. This is a team just for XRISM. I've got one team photos here for all the other Astro missions going back. So these are some of the boats. This is, I think everybody knows this spot here at Goddard in Building 7, right? And since I knew I was going to see some friends here, that's my pictures. So there's Tony, right? People know who this gentleman is? Tom Margulies, who sadly passed away. He was our mission manager S32. And Herb Middleman, over there on the right. This is in the so-called CRIF of Building 7. That's Chuck Kelley, is one of our team members there. And this is another part of that day. I think we know who this guy is here.
No, hasn't changed a bit.
I wanted to just point out John Leon. John Leon was our instrument manager back on SU2, really fantastic instrument manager. I understand he was hopefully going to be here today, but he couldn't make it. There's Tony again, and I think that's Reber, Center Director. And Nick White, White's on the right there.
Yeah, okay.
And another person you might remember from all the days, Mike Stavich, here in the middle. He got his start, I think, at Goddard in the cryo branch. I was back watching Kobe being built. He was very much part of that world. Okay, so I think that's, and just Nicholas there, we're kind of a candid shot I took one day of them going over. Okay, so thank you very much. More further questions?
There was I had a question. So I recall there was an issue with one of the filters on PRISM. What was the loss to the science of
Okay,
that
let's
filter?
bring that up after the just there is on the door. There is a door that normally is closed, so you can go over ground distance. The door has a very high vacuum, level of vacuum inside. And so the idea is actually get in space, you open the door, and you let your x-rays in. That door did not open. There have been many attempts to try to deploy the door, it did not open. So how are we getting data? The reason we have data, fortunately, is there's a beryllium window on the door. So x-rays above about 2 keV, 2 kilovolts, get into the instrument, and we're fine above that energy. So we are missing a key part of the spectrum, which is from 2 keV down to 0.2. There's a lot more science we could be doing. The lower Z elements, so oxygen, nitrogen. There have been several attempts that try to open it. In fact, using elevated vibration from the mechanical coolers to try to open it. And we just did a recent attempt back in October, September last year. And unfortunately, that didn't do it. So it's a setback for sure, but it's not it's not mission ending.
Good. Thank you.
You're welcome.